Hello friends, and welcome back to our online tutorial for today. And I'm your host James Ela, popularly known as Sot. We shall continue. I believe we are still looking at the first bunch of notes which were sent to RAS, which is on sets. I believe specifically this is more straight tutorial to the School of Business. Those in the School of Business, BBBAC, Banking and Finance, Human Resource, those doing Human Resource, those doing Economics, those doing Transport and Logistics. In short, we're talking about the mighty Business Mathematics, which is the course code 140 at the Copperbelt University. So we are still looking at the first bunch of notes, which is on sets. I believe we made an intro of sets last time, what sets are, and we even looked at specifically on sets of numbers, where we had to define some of the terms such as what a natural number is, a whole number, irrational numbers, rational numbers, integers, and so forth and so forth. And I believe if those who went through the previous notes and as well as the previous video, we had to put our emphasis most on the part of rational numbers and irrational numbers, where we did some of my examples involving these two concepts. So today we move on and look at something else. Today we are going to look at the concept of surds and radicals. So today we are looking at the concept of surds and radicals. I believe it's not our first time hearing the word surd, or maybe hearing the term a radical. So if it is your first time, try by all means to stay glued to this video. Try going through it, and you'll be able to understand the meaning of surds and radicals. Okay, so let's go into business by looking at maybe the definition of a surd. Look at the definition of a surd. We can try to define it in simple terms so that every one of us can be able to understand this term. What is a surd? So I believe if you have gone through the previous video, you understood what a rational number is and what an irrational number is. So now, in defining a surd, I'm going to get the idea of us knowing what irrational numbers are. So if you're able to know what an irrational number is, you'll be able to understand clearly on what a surd is. So basically in this case, we can simply define a surd in simple terms as, we can define a surd as this is an irrational number. This is an irrational number that cannot be expressed as a finite decimal or fraction. Remember what an irrational number is? A number which cannot never be expressed complete in the form of a over b, where a and b are integers and b is never equal to 0. So that is the same concept we're trying to embrace here. It is to say a surd is an irrational number. So we're simply saying that a surd is an irrational number that cannot be expressed as a finite decimal or fraction. So in other terms, another term, we can just simply say that this is just a root of a number that cannot, this is just a root of a number that cannot be simplified. that cannot be simplified to a fraction. So if you just take, for instance, a root of a number that cannot be completely be simplified to a fraction, that is a surd. For example, if I simply say the root of 2, you believe with me, maybe we will simply agree that the root of 2, if you are to punch root of 2 on a calculator, you'll discover that this number will still, the decimal numbers, maybe the decimals are not something which can be finite or which can be counted. It is something which is continuously, or maybe a non-terminating decimal, which qualifies it to be called an irrational number. Remember what we said about irrational numbers. Most of irrational numbers have decimals which are non-terminating decimals. It will still continue be moving 1.1 blah 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 blah, and we don't know. It is non-terminating. This is an example of a surd. Maybe we can simply say root of 5. It is an example of a surd. The same, maybe root of 3. It is an example of a surd. It has non-terminating decimals. That's the concept, or that's the idea of what we are supposed to be able to understand about surds. Okay, maybe we can talk about maybe types of surds which we are supposed to be able to understand. Types of surds. What are some of the types of surds you're supposed to be able to know? So we have the first one. We can simply call this surd to be quadratic surds. Quadratic surds. So surds which are in the form of square roots, these are quadratic surds, and so forth. So square roots surds. Surds which we can simply call cubic surds. Surds with the power of 3. So surds with the power of 3, maybe we're talking about them to be cube roots. If I simply say cube root of 2, this is a cubic surd. Cube root of 5, it's a cubic surd. Cube root of 7, it's a cubic surd. And then at the same time we have higher order surds. So by higher order surds, we're just simply saying that these are surds with a highest power more than 3. So for example, maybe we talk about the fourth root of 2, that's a higher order surd. Or maybe we can talk about the fifth root of 2, that's a higher order surd, etc, etc. So basically this is the idea which we have to be able to understand when it comes to concepts of surds. So when it comes to concepts of surd, this is an idea we're supposed to be able to understand. Okay, this is a surd. What about if we bring in the concept of radicals? Basically the surds and radicals, there is no much difference about them. Most of the times, even most mathematicians sometimes confuse them to be just one thing, to say okay, a surd is a radical and a radical is a surd. But in most cases we can try, when you talk about radical number, a radical number is simply called a surd. So but let's try to define separately what we mean if we simply say a radical, maybe in that context. So we want to understand what a surd is and what a radical is before we go into some of the operations. So I'm going to talk about radicals, what a radical is. What is this radical which we're talking about? So basically when it comes to radicals, a radical is simply a symbol used to represent roots of numbers. So when it comes to radicals, when you hear the word radical, when it comes to radicals, we're just simply talking about a symbol used to represent roots of numbers. For example, what kind of symbols are we talking about? To represent roots, we're talking about representation of roots. So what kind of symbols are we talking about? We're talking about square root, we're talking about cube root, we're talking about fourth roots, we're talking about a number of radicals. That's just like the way types of surds, the types of surds we have. We also have types of radicals. We also have types of radicals. We have types of surds and also have types of radicals. So the types of surds, we simply said we have quadratic surds, same as types of radicals. So when it comes to types of radicals, we still have the same types of radicals, which is quadratic radicals, which is cubic radicals, which is higher order radicals. And I believe we understand all this. So quadratic radicals, we're talking about a radical with the order of 2, maybe the power of 2. Cubic radicals, we're talking about radicals with the power of 3. And higher order radicals, we're talking about radicals which has the power which is greater than 3. That's the concept which we have to understand when it comes to radicals and surds. Now, with this idea or this concept, I want you to understand that if I write a radical number or maybe a surd in the form of maybe square root of a, remember a represents this number under the root. So in short, this is a surd. This is a surd. Remember how we defined a surd. So this is a surd. This is a surd. So now, if this is a surd, joining the concept of surds and radicals, what are we trying to say? We are simply calling this guy, this root, this sign, to be what? A radical. Remember, we simply said a radical is a symbol used to represent roots. So this sign here, which is the root of this a, this guy is called a radical. Now, what about this guy under the root? Under the root, the guy under the root here, we are calling this guy to be called a radicand. So that is a brief, well explained and well summarized concept under surds and radicals. So the whole number is called a surd, the sign is called a radical, and what is inside is called a radicand. That is the idea of surds and radicals. Now, I want us to move on to some of the properties which will be able to help us simplify some of the surd expressions and some of the radical expressions which we might have. So what are some of these properties which will guide us? Properties of surds or radicals. So when it comes to the properties, we are simply saying that let A and B be real numbers. So A and B are just basically real numbers in this case. Then these are the properties that are going to be able to understand or maybe be able to follow through. So the first property which is going to guide us is that if A and B are real numbers and then you have a scenario or a case whereby you've been given the root of A, which is multiplied by the root of B. So maybe you've been given a certain expression to say, can you simplify this? Root of A multiplied by root of B. So this is just as good as simply saying that the same root, and take the real numbers, which is A and B, multiply them inside that root. So root of A multiplied by root of B is the same as the square root of A multiplied by B under the same root. So remember, A times B can just be written as AB. I believe we understand this concept. So now, this property is only applicable if we have the same radical. This property is only applicable if we have the same radical. The same is happening in a case whereby if I have cube root of A multiplied by cube root of B, I still have the same radical. This is a cube root and this is a cube root. This will be just as good as simply saying cube root of AB in there. This is a square root and this is a square root. No wonder the outcome is just the square root of AB. If it was a fourth root and the fourth root, it will still be the same. But in a context whereby you have a cube root and a square root multiplying, this idea will not work out. That's one thing we're supposed to understand. So as in the idea here is that if A and B are real numbers and they have a root of A multiplied by a root of B, provided that these are the same roots, I'm just able to multiply these two numbers under the umbrella of that root. Second property which we are going to have here, the same, this is multiplication, even division is true. So if you have the root of A divided by the root of B, if you have the root of A divided by the root of B, what is happening here is that is the same as, remember division, you can write it in this format or you can write it in the form of root of A over root of B. This is the same case, both means division. So if this is the case, this is just the same as dividing the two real numbers under the same root. So we have A over B. So you can have a situation whereby you have root of A divided by root of B. If provided that these are the same radicals, just divide these numbers under that root. It's the same idea. And we have the third property which you can go ahead and use. This property can be as if you have the root of A multiplied by the root of A. What do you have here? This is the same side multiplying with itself. The side multiplying by itself. So root of A multiplied by root of B. A. So with the, where am I going to base this idea from? Based on the first property. The first property said that if you have two real numbers, or maybe two radicals or two sides with the same radical, it is just as good as multiplying them under that radical. I have the same radical here. This is just as good as what? Multiplying them under that what? Radical. So this is A times A in there, and this will just lead us to what? The root of A squared, which is going to lead us to what? Square root of A squared. It is just as good as what? A. So no wonder we're simply saying that root of A multiplied by root of A, it is just as good as what? A. So if the sides multiply by itself, the radicals will cancel each other and just maintains what is inside there, and we just have the radicand, which is A. If two surds, a surd multiplies by itself, the radicals Z will cancel each other. So this is the concept we're supposed to be able to have. That's the idea we are supposed to have, or maybe some of the three main properties you're supposed to have, even when as you will be simplifying radicals or surds, be able to have this idea, this concept concerning surds and radicals. Yeah, so let's look at an example concerning simplification of surds. You can have example concerning simplification of surds. So this example, you can check it out in the notes we sent you, in the first bunch of notes we sent you, which you are simply saying that simplify each of the following. Simplify each of the following, leaving your answer in surd form. So you can check the same example in the notes which we sent you, the first bunch of notes under sets. So where we'll be simplifying these expressions and we're going to be leaving our answers in surd form. So if that is the case, we have the first expression where we're being told to say we're going to simplify the root of 20 plus 2 root of 45 minus root of 8. So that's the first expression we're going to simplify. So there are some cases where you're supposed to be able to understand the mathematical terms which are being used. When they tell you to simplify, what does it mean? Simplifying is just coming from the context which means make it simple. So the way it is, this expression, as you are looking at it, it is something which is very a little bit complicated. So what are they trying to say? Please make it simple for us to understand. So if you were to get this expression, make it simple such that if you were to give a grade 8, the person will be able to understand. So this expression was simply basically this in the actual sense. As simple as that. So how am I going to simplify this so that a grade 8 can be able to understand that this context or this expression is basically something which is simple, a simple version of this. What does this represent? So if you have root of 20 plus 2 root of 45 minus root of 8, what does this basically mean in a simple version? So let's simplify it. So we're going to have, what are we going to do? So we basically here we're going to use the same concept, or maybe the properties we talked about in the first place. Issues of multiplication, issues of division, and the like of these surds. So those concepts or those properties which we've said, these three properties, are going to apply them in this. So what we're doing here is we're going to break every surd into its simplest form, such that when it seems when using the operations, some of the operations, we are going to make a simple version out of it. So the context here is use the properties to break these surds. So what are we trying to say is use the properties to break down the surds. Use the properties to break down the surds. Remember, we simply said root of A by root of B is the same as root of A by B under that root. So this is the same thing I'm going to do to each case. I'm going to break it down to something which is simple, which I'm going to things which can be simple in a simple version. We're going to be breaking it down. So in the breaking down, I want to understand that the inside I need to have something which is more like a perfect squares. I need to bring out more like perfect squares from that surd. For example, we're going to break down the root of 20 to something. We're going to break down the root of 45 to something, and we're going to break down the root of 80 to something. These are the surds which we have in this expression. So let's break them down. So we're going to use that broken version so that we are able to simplify them out. For example, if I look at a 20, wow, using this property, how can I break this 20 to suit this property? But I'm trying to break it down so that I can have a perfect square in this 20. A perfect square in this 20. There are a number of ways we are able to break down this 20. Remember, you can have 10 times 2. 10 times 2 can be able to give you a 20. But 10 and 2, both of them are not perfect squares. I hope you are able to understand. 10 and 20, if you look at, 10 and 2, the square root of 20 is not a perfect, something perfect. Or maybe square root of 2 is still not something perfect. We want to break it down so that we can have something whereby when we square root it, we're going to have an actual value based on this property. So basically 20 with this property is the same as the square root of 4 by 5. Wherever I use 4 by 5, I can use 10 by 2. I can use 20. I can use what else can make 20 apart from 4 by 5? Yeah. So there's a 4 by 5. There's 10 by 2. But I've not chosen 10 by 2. Why? 10 and 2 are not something which will give me a perfect square, a perfect root. I believe we're able to get. But 4 and 5, there is something which will give me something which is perfect here. So 20, root of 20 is the same as root of 4 by 5, which using this property, this can still be as root of 4 multiplied by root of 5 using this property. Remember, we simply say that if A and B are multiplied under that same root, it is just as good as breaking the two roots to be independent. So 4 by 5 under that radical, it is just the same as the root of 4 multiplied by root of 5 based on this property. Hope we're able to get the idea there. So if you look at now, this root of 4 by root of 5, this is just the same as saying root of 4 is something which is perfect. What is the square root of 4? The square root of 4, it is just as good as what? A 2. But root of 5 is not perfect. So it not being perfect, I'll just write it as what? 2 root 5. Okay? So that is, in short, we are able to see that root of 20 has been broken down into something simple to become 2 root 5. So this root of 20, instead of me using root 20, I'll be able to use 2 root 5. It is something which is simple version. The same, whatever I've done here, is the same I'm going to do to lose root 45. So root 45 again will be broken down into something which is 2 factors in it. Remember, root 45, according to this property, I'm going to have two numbers whereby if they multiply them together, they'll give me a 45. But those two numbers, one of them should be something which is perfect, such that when you square root it, it will give you something perfect. It should give you something whole number, which is a perfect square. We're talking about perfect squares here. I believe you're able to understand when it comes to perfect squares and the like. Yeah. So there are a lot of numbers whereby when you multiply them, they'll give you 45. But you're just looking for those specific ones specific ones. So these specific ones we're talking about, if I'm looking for a 45, I'm looking at a 9 multiplied by a 5. And you agree with me that the square root of 9 is there, something which is perfect, no decimals involved. Just like we did here, 4 times 5, this 4 is a perfect square. It's a perfect square. 4 is a perfect square. Square root of 4 is just basically 2. Same applies with 9. 9 is a perfect square. Square root of 9 will give you a 3. So no wonder we're trying to break down these. Have it with the, at least we need to have perfect square involved in that breaking down. So this is just as good as root of 9 by 5, which is the same as saying root of 9 multiplied by root of 5. And root of 9 multiplied by root of 5, what does that mean? We are able to find the square root of 9. Finding the square root of 9, this is just basically 3, which is the square root of 9, multiplied by root of 5. I'm still maintaining the root of 5. Why? Because 5 is not a perfect square. It is to be maintained to be a surd. Let's handle the 80. How can I break down this 80? There are a number of ways we are able to have 80. 10 times 8, but is 10 and 8. Can I have a perfect square on 10 and 8? No. There are a number of ways. 40 by 2. 40 by 2, are these two perfect squares? No. We are looking for something which should be perfect. No wonder the 80 can be broken down to have something like 16 by 5. And 16 by 5, you agree with me that 16 by 5 will give you something like 8. And 16 is a perfect square. The square root of 16 will basically give you what? A 4. So we're looking at, in this breaking down according to this property, we're looking at something which is perfect. So that when you simplify this, it would be something in a simple version. The essence of all this is for us to be able to simplify it and have like terms in this expression. Right now we don't have like terms. No one, it is very complicated. But we want to simplify it. We have like terms in it, and be able to have something simple. So this is basically the root of 16 multiplied by the root of 5, which is the root of 16 is a 4. Root of 5 maintains to be the way it is because it is the surd. Now let's now join these two. Let's now join all these together. Now let's join all these expressions together according to what we had. So remember, we're trying to simplify the root of 20, root of 45 minus root of 8. How do I simplify this? The root of 20 has been simplified to what? 2 root 5 plus, we have a 2 here, 2, but the root of 45 has been simplified to what? To 3 root 5 minus the root of 80 has been simplified to what? 4 root what? Root 5. So basically, what do we have here? What we have here, we have something which are like terms. Remember, like terms, they're able to be added or subtracted. So simplifying this is just the same as 2 root 5. This 2 and this 3 are able to multiply. 2 times 3, I'm going to have a 6 root 5 minus a 4 root 5. Now there's something similar on these three terms. There is a root 5 on each, which makes them to be qualified to be called like terms. They can be added or be subtracted together. So regarding this root 5 more like to be an x, maybe we have 2x plus 6x minus 4x. They're able to be added or subtracted because there's something similar on each. But if I had something different, maybe there's a root 6 here, root 3 here, and root 4 here, it can't be added or subtracted because they are complicated, they are unlike. So what am I going to have? I'm going to just have 2 root 5s, add them to 6 root 5s. So in short, you have 2 spoons plus 6 more spoons. What are you going to have? You're going to have something like 8 root 5. This one brought down minus 4 root 5. 8 spoons minus 4 spoons. Remember, the root 5 is taken to be more like something more like a spoon. It's something similar on each term. So 8 minus 4, we're going to have something like 4 root 5. So basically, this will be our answer. So if you look at this expression, it has been simplified to something simple, which is 4 root 5. This is just basically equal to that. No wonder the question said that simplify this, which you'll be looking at, which will look like something like such. So if you were to give this to a grade 8 to be put on head, it's just the same as that. Something which is very simple and straightforward. Yeah. Second example, which we can look at. The second example can simply say, simplify the root of 12 over the root of 156. The root of 12 over the root of 156. The same concept, the same idea, but this time around we are using the concept of division. Recall the property we said that root of A over root of B is the same as root of what? A over what? Over B. It's the same concept, same idea. That's one thing you're supposed to be able to understand. But yeah, so if we want, we can still write them all under the root and be able to simplify whatever we can simplify and the like. So with the same thing we did with the previous example, what are we doing? We are breaking every surd independently and then simplify at the end. Break every surd independently and simplify at the end. So you break your root 12 and you break your root 156 and simplify at the end. Remember, in your breaking, you're supposed to have something which is a perfect square. 12, for it to have a 12, you need to have 2 numbers to multiply to give you a 12. But one of them should be something which is a perfect square. 156, you need to have 2 numbers to be multiplied to give 156, but one of them should be a perfect square. There are a lot of numbers, but basically concentrate on numbers which are perfect, which is a perfect square. So we're simply saying that root of 12 over root of 156, this basically is the same as breaking down the 12, 2 numbers which can be multiplied to give us a 12. One of them should be perfect square. We can have 6 by 2, but 6 and 2 are not perfect squares. So we've chosen 4 by what? 3 over root of what? Breaking down the 156 into 2 factors, which will be multiplied to give us 156, but one of them should be a perfect square. What are those numbers? We can talk about 4 and 39. We're just talking about factors. If you want, you can just list the factors of 156 and then be able to check which one can I use. Remember, one of them should just be perfect squares. And then if this is the case, what is the idea here? This, according to the properties of multiplication, remember, we simply say that this can be that, or root of A by B is the same as root of A by root of B. This is what is going to even happen here. So if I have root of 4 by 3 inside here, separating the two, I'm going to have root of 4 by root of 3. over root of 4 by root of 39. Okay, and then from there, what do I have? Automatically, this is division. This is root of 4 multiplied by this. It means that this and this can go. And what am I going to have? Basically, I will just have something like root of 3 over root of 39. Is it done? Nope, it's not yet done. We can still break down something here. I believe the 39 can be broken down into something nice. 39 can be broken down into something nice. Two numbers which can be multiplied to give us a 39. But yeah, two numbers which can be multiplied to give us a 39. Remember, I want to simplify this further. So we can have something like root of 3 over this 39. We can have 13 by 3, I think. Yeah, 3 times 3, that's a 9. 3 by 1, that's a 3. So 13 by 3 will give us a 9. Remember, because of this root 3, I can understand that they can be, obviously, must be root 3 coming out from the denominator, so that root 3 in the denominator can cancel out with the root 3 in the numerator. So I'm going to have root of 3 over root of 13 multiplied by root of 3. This and this will go, and I'm going to have a 1 in the numerator. I'm going to have a 1 in the numerator over root of 13 in the denominator, and this will be the end of my expression. So root of 12 over root of 156 is just as good as it being 1 over root of 13. As simple as that. So that's the concept under surds and radicals. That's the concept under surds and radicals. So now, just take a homework or maybe a task I can give you under surds and radicals. I want you to simplify this one and leave your answer in surd form, or maybe a task. I can give you a task or homework. How do you put it? Yeah. So simplify this one. Simplify and leave your answer in surd form. So I want you to work on this one, which is root of 11 minus 5. These are closed brackets, another open bracket, 5 minus root of 11. So just simplify this one. What is it going to be? I just want you to simplify it first. So this is something which has, so hint, expand. Expand by breaking the brackets. And then simplify. That's a hint. So you can work out this one and be able to send in your solution just as you have been doing. Yeah, so simplify that one, leave your answer in surd form. Yeah, thank you very much. The next part or the next tutorial video which we are going to post will be something on rationalizing. Yeah, since we are able to have an idea of the concept of surds and radicals, and then later on we're now going to look at rationalizing. Yeah, thank you very much and blessed day.